Once again, just please, whatever you do, just review. Just review a little bit here. So long as you review a little bit, things are going to go beautifully. I remember last year, wasn't this chapter the one after this you absolutely have to review? I remember it was a particular student that I asked a question of one of our class. I was like, no matter what, for this next chapter, chapter 17, gotta review every night. If you do, things are gonna go easily for you. I asked the student, I was like, hey, class, I asked them a specific question, and nobody raised their hand except for this one student. And when she gave the answer, it was spot on. And I was like, how did you know the answer to that problem? She said, because I did exactly what you told me to do. I've been reviewing each night, and everybody else in the class looked at her like, wow, we wish we would have done that. The key is the material is not difficult, but it is going to be, once again, if you do not go back and just review on a regular basis. All right, here we go. So we'll talk about acids and bases. A brief introduction to acids and bases. We'll talk about Arrhenius acid, Brønsted Lowry acid, autoionization of water, and we'll talk about the pH scale as well. So first thing we're going to talk about is we're going to talk about what is a acid. Keep in mind, when it comes to these chemicals that we'll be working with in this class, chemicals are going to fall into really one of three categories. Either that chemical is going to be classified as being an acid, it could be classified as being a base, or it's going to be classified as something being neutral. It's going to fall in one of the three categories in this case. And eventually, we'll be able to figure things out by just looking at, in this case, the actual structure of the molecule. And you'll say, hey, based upon this structure and the way it interacts with water, you're going to be acidic, or you're going to be basic, or you're going to be neutral. And that's one of the things we'll take a look at. So what we're going to do is we're going to first start off by the basic definition of what is defined as being an acid. And the first person to kind of come up with this concept of an acid was Arrhenius, Savitri Arrhenius. He's also responsible for that activation energy barrier. Remember that thing? He was the person. He did a lot of chemistry here. What Savitri Arrhenius simply said is that, hey, when it comes to an acid, that an acid is going to have the characteristic of being something that is actually going to be sour. And if you think about it, anybody ever had those like sour heads or sour apple candies or any of that stuff? If you ever had it, if you look at the actual ingredient, it's going to say something on the back of it that says citric acid. And that's what's giving it that kind of sour taste. Even if we think about things such as lemons. Anybody have lemon juice on a cut? Kind of hurts, doesn't it? Yeah, that lemon juice is really acidic. It has a high concentration of citric acid in it. A lime is not quite as sour. Guess what happens to the concentration of citric acid? It's a little bit lower. An apple has a little bit of citric acid as well. It's actually even lower. So it has a tendency of kind of tasting sour in this case. It can also take and change dyes different colors. And we'll talk about that when we start looking at indicators here. So vinegar is a prime example of something that's extremely sour. And what it has inside of it, it has acetic acid inside of it. And it's only normally about 1% acetic acid, and 99% of the vinegar that you're buying is nothing more than water. But that little itty bitty 1% makes that thing extremely sour. Now in my acid cabinet, I got concentrated acetic acid. That stuff, if I open it up, which I wouldn't do in the classroom, I always open it up in the fume hood. Because if I open it up in the classroom, oh my goodness. The strength of the acetic acid and how pungent that sour smell, yeah, you wouldn't want to smell in this case. But once again, it has a tendency of being sour. The next thing we'll talk about is bases. You figure out that bases have a bitter taste to it. This one's a little bit harder for me to describe. Has anybody ever had their mouth washed out with soap? Have you ever heard of that saying? Like if you had a foul mouth that your parents would wash your mouth. Anybody in this classroom?
My brother has.
Your brother, you gotta throw him under the bus. But nobody in this class? Man, this is great. Every year I have somebody who raised their hand like, okay, in the shower. All right, but clearly, this is great because last year I had like 5 or 6. I had to give them a hard time. I was like, man, you must have had a very potty mouth when you were younger. But clearly, this class never used those sort of words. But typically, if you did say a bad word and your parents kind of wash your mouth out with soap, soap once again has a bitter taste to it. But one of the things that I know about soap or about bases is bases have a tendency of actually being slippery. A lot of times, if I'm working with a chemical and I'm not sure if it's water or if it's base, I'll just take my fingers, I'll do this. If it's slippery, then I know it's a basic solution. If it's a basic solution, I know I'm gonna neutralize in this case. Bases, I don't like to play around with. Because one of the things that will happen with a base, just to point this out to you, is say I get some sodium hydroxide. So here goes my arm right here. Got a little muscle there, got a little, small little bump there. All right, say I get some NaOH here, sodium hydroxide, which is a base, and it's on my arm. So I got a little bit on my arm here. Even if it's not concentrated, so it's really dilute, so it's not really burning me. High concentration sodium hydroxide, oh, absolutely burn you pretty quickly. But let's just say it happens to be dilute here. So I got sodium cations, I got the hydroxides. As the water starts to evaporate, what's going to happen to the concentration of the sodium hydroxide? It's going to go up. And then it's going to continue to go up until the concentration becomes really concentrated. And then it's going to start to burn you. How do I know this? Because I had it happen to me when I was in grad school. I got some sodium hydroxide on my arm, unbeknownst to me, didn't realize it. Started to feel a little tingling, a little bit more tingling. And I looked down, and next thing I know, I'm like, and I'm trying to put it under water to try to neutralize in this case. I got a little itty bitty scar on my arm from the sodium hydroxide. I actually kind of burned my skin in this case. Sodium hydroxide is actually capable of dissolving human tissue. So you gotta be careful, especially as it starts to get more and more concentrated. So once again, if you do get sodium hydroxide on your skin, the thing that you wanna always do is you always put vinegar on it. Why do we put vinegar? I'll explain it, but it's because it's a weak base in this, a weak acid, I'm sorry. And it will neutralize it. I don't want to go with something like hydrochloric acid and splash it on there, because it'll neutralize it, and then it'll be really acidic, and then it's going to end up burning me. But if I pour the vinegar on there, it'll neutralize it. Because the vinegar is so weak as an acid, it's not going to burn me. We'll take a look at this a little bit later on. So once again, some examples of base could be something such as soap here. Now, when it came to Arrhenius' definition of an acid, the way that Arrhenius decided to define an acid was he simply said that an acid is going to be a substance that's going to have the ability to contribute a high hydrogen ion when dissolved in water. So one of the things that we're going to see when we start looking at acids is we're going to see things such as this here, like HCl. We might see something like H2SO4. We might see something like HNO3. We'll kind of see these things going on right here. And what just happened there? There we go. So acids are going to kind of start off with this H+. And once again, if I take something like HCl, and if I dissolve it in water, it's going to end up doing something like this. It's going to produce H+, aqueous, plus Cl minus, aqueous as well. So there it goes. It has the ability to produce the H pluses here. Bases have the ability to produce the hydroxide ion. That's why way back in honors chemistry, we said things such as sodium hydroxide. If I take this and I dissolve it in water, then it's going to end up producing Na plus aqueous, plus it's going to produce the hydroxide anion. Oh, I got something that is going to be basic right here. So all we're really looking for is we're looking for something that's acidic, that's going to look like this, HX, kind of aqueous here. And for the base, it's going to be some metal, because that's an anion, and hydroxide, aqueous. So by definition, that's all we're looking for, to kind of figure out if you're an acid or a base. Also, don't forget, we have this common saying that an acid plus base yields salt plus water, which means that if I take an acid, so here goes hydrochloric acid. I react it with a base, sodium hydroxide. All it does is go through a double displacement reaction. Hey, do-si-do. Hydrogen cation goes with the hydroxide, produces the water. Sodium goes with the chloride to produce my ionic compound. Remember, we said an ionic compound is going to be a salt. So acid plus base yields a salt plus water in this case. All right. Now, one problem we have is that when it comes to Savitri Arrhenius' definition of an acid, the problem that he ran into is that it didn't capture all the things that might be acids and also bases. there were some things that just did not start off in this case with an H plus, or maybe have the hydroxide of a part of it. But yet we still found out that they happen to be, in the case of an acid, or maybe a base in this case. To give you an example, is that if we look at something like ammonia, when you look at it, is actually going to end up being a basic solution. If you get ammonia on your skin, it will become slippery in this case. His definition and the way that he went about looking for these things, such as, hey, acid starts with H plus, base starts with hydroxide, it just missed it. Couldn't capture everything. So there had to be just another way in which we can actually look at this thing. And what they were able to figure out in this case is that, hey, you know what? Maybe we should look at it from a broader definition. And this is going to be what is called our Brønsted Lowry's definition of how we're going to see an acid and also a base. And what Brønsted Lowry decided to do is they said, you know what? Forget about this starting off the H plus and having a hydroxide. What we are going to focus on strictly is that hydrogen cation. And when it comes to the hydrogen cation, we're going to go in and simply say that whoever is donating the H plus will be defined as being our Brønsted Lowry acid in this case. So the person who provides that H plus is going to be the acid. The person who is going to take on the H plus is going to be defined as our base. Which means that if we look at kind of this definition is going to allow us to capture everybody. And if we look at a good example here, say I've got something such as HF. Well, under, in this case, Arrhenius' way of looking at it, I would have said, you know what, you're an acid. And we're still going to see it as being an acid. Because if I look at it, in this actual equilibrium that's going to take place here, this H plus is going to transfer itself over here to the ammonia. You are the hydrogen cation donator. You over here are the hydrogen cation acceptor. So I can go and say you will be the acid, and because you're accepting the hydrogen cation, you are going to be classified as being my base. As simple as that. Whoever donates, acid, whoever accepts is going to be the base. Now, you might hear me say that, hey, the acid donated a hydrogen proton. Hydrogen cation is going to be this thing right here, H plus, which is also referred to as a hydrogen proton. So sometimes they'll call it a hydrogen proton, sometimes they call it a hydrogen cation. Same thing, synonymous. Why do they call it a hydrogen proton? Well, let's just think about hydrogen for a second. If I look at elemental hydrogen based upon the periodic table, this is like 1.008 down here. How many protons does neutral hydrogen have? One proton, right? So just neutral hydrogen, no charge, has one proton. How many electrons does it have? One electron. How many neutrons does it have? 0 neutrons. If I take away the one electron, then what do I really have staring at me? A proton. Hence, they sometimes call this thing just a hydrogen proton. We'll use it synonymously. Sometimes you'll hear me say hydrogen cation. Sometimes you'll hear me say, oh, it donated a hydrogen proton in this case. All right, here we go. Moving forward. Now, in this reaction that I have up here, you'll notice that I've got the following kind of playing out here. I've got my HCl. And when I look at this reaction, you'll notice that the H plus, my hydrogen cation, is being donated, in this case, to my actual water. So I can go over here and I can simply say, you are my acid, and you are going to be my base in this case. Gotcha. And what you're going to end up producing is you're going to produce this thing called H3O+, which I should have in the notes right there. It's called the hydronium cation. That you got to be familiar with. You're going to hear that pretty much throughout this whole entire chapter. It's going to be real hydrogen or hydronium cation. Now, one thing to point out in this case, if I go get my hydrochloric acid out of the cabinet, and when it's inside of water, it does produce this. I'm here to tell you, this is really important. Do not forget this. When I have an acid, so here is my acid. I'm going to put it this way here. HX aqueous plus H2O liquid, because the acid is always going to be kind of dissolved in water here. It's going to produce, in this case, H3O plus aqueous, plus it's going to produce some X minus aqueous over here. I am not afraid of you. That's not what's going to burn me here. What I am afraid of is this right here. That is the stuff that when I get it on my skin, it is going to burn. Why do I point this out? Is we're going to start seeing things such as strong acids. And remember, back, all the way back, first semester. Remember we had to learn about the strong acids? And we said strong acids 100% dissociate, which means that all of this, when things are said and done, this is gone. All we got is this over here. So I'm gonna have like 100% of it looking like this over here. Now, if I look at something such as a weak acid, watch this. When it comes to a weak acid, I'm gonna have something, I'll call this maybe HY, aqueous, plus H2O as a liquid. It's gonna donate that hydrogen cation over here. I'm gonna end up getting, in this case, a smaller percentage, so H3O plus aqueous, plus I'll get Y minus over here. Maybe I got something like this here. 10% here, 90% over here. How is it possible that I can get like a lot of it still on this side over here? Where would I probably need to sit right here?
Equilibrium.
That's exactly it. And what you're gonna see, and sometimes in equilibrium we like to do things such as this, and you might see it in textbooks sometimes. And all I'm simply saying is that, yeah, you got a little bit going over this way, but a lot of it's over here. Yes? How did what? How did I say it one more time?
I have to leave at 11.
Oh, you gotta leave at 11 o'clock?
11:30.
Oh, 11:30? Well, I got one more minute with you. Man, you can't leave early. One more, 30 seconds. Get out of here, go. All right, here we go. So what we can see is that if we have an equilibrium, then I can have now a smaller percentage of this down here. Meaning that once again, this, I'm not too afraid of this, especially as it becomes weaker and weaker and weaker. And when it comes to things like vinegar, you might be down here like maybe the 1%. But then we got other things that's 10%. And as it becomes stronger and stronger and stronger as a weak acid, I get more and more fearful because once again, it's the hydronium cation that's gonna be a thing that's gonna end up burning me. Not this over here. That's gonna be important. Eventually, we are looking at the actual strength of the acid. We're gonna calculate things such as our pH, always based on these things here and not down here. All right, one thing just to point out, what you're gonna see happen in this chapter, something is going on with my power cord here. And I think my power cord has decided, you know what? Give me 1 second. Luckily for me, I have another power cord here. All right, in the notes, right underneath of this, you're gonna see something that shows this right here. There he goes. It's gonna come back. There we go. You're gonna see something that looks just like this here. HCl aqueous. And it's gonna go like this. H plus aqueous plus Cl minus aqueous. You see that in your notes right underneath of it? It shows that reaction. And above it, we have this reaction. HCl aqueous plus H2O liquid going to produce H3O plus aqueous plus Cl minus aqueous. Keep in mind, both of these are the same. They're going to be the same. The only difference between them is this is more factually correct here. I'm going to show you how this is playing out. However, a lot of times in chemistry, they might shortcut it, where they're going to pull the water out. Pulling the water out is still going to be okay, because it's not going to change anything if we pull the water out, especially when it comes to equilibriums. Products over reactants know who? You're not making it to the equilibrium expression anyways. And that's why sometimes they'll show it this way. This is a truer, correct picture of what's actually taking place here. When I take something such as hydrochloric acid, so here goes my picture here. H plus, connected to some F minus right here. I've got water here. H2O, right? So it looks something like this here. That's my H right here. And this is my oxygen. What will happen in the actual reaction is the hydrogen will donate itself over here. And what you're going to end up with is you're going to end up with this thing right here, H. I'm putting a hydrogen cation here, which is now H+, which means overall this whole entire thing is +1. And then of course I'm going to have the F- as well, kind of being by itself here. So really what's going on is the hydrogen cation just dumps itself onto the actual water. What this picture is showing right here, it's just simply saying that you're going like this here. Oh, and that should have been Cl, I'm sorry there. We're working on hydrochloric acid, HCl. Stick with it, be consistent. What this picture simply says is that what we have here is we got H, we got Cl here. And then what's going to end up happening is it goes and it produces H plus Cl minus here. This H plus and this hydronium are the same thing. We just use them interchangeably. This is kind of like our shortcut way where we remove the water from the whole entire equation. And this is where we show the water. For most of the problems in this chapter, I'm going to show you the water, because this is truly what's going on. That hydrogen cation is really not out there by itself. It really dumps itself on the actual water. One of the things that you'll see, don't write this part down, but eventually we'll calculate the pH. We'll say, hey, the pH is equal to the negative log, don't write this down, of H+. Or we'll say the pH is equal to the negative log of the H3O+. They're the exact same thing. I don't care if you go this way in which you treat the acid, or whether you go this way where you treat the acid. You will get the exact same answer. Just here, if we go with this equation, I'll plug in, hey, that value. If I go this way, it's going to be the exact same number. I'm just going to say, oh, I'm looking at it from the hydronium cation. So the H+ and the hydronium cation, they are the same thing. It's just one shows the interaction with water, which is the true way in which things take place, and the other one is not in this case. All right. And you'll kind of notice right here as well, man, look at that. That is a beautiful picture there, actually. I never noticed that. Wow. Why is their picture actually more attractive than my picture right here? What does that kind of show there?
Correct molecular orientation.
I'm telling you girls are just geniuses around here. You're absolutely right. You know how many gentlemen will probably look at it and be like, I don't see it, I don't see it. You're the correct, proper molecular orientation. And in honor of Savitri Arrhenius, who was the first person who talked about acids, what else does it must have in this case? Proper orientation and activation energy to break the bonds. And once again, you'll get the hydronium cation, and you'll get, once again, the chloride here. Or we could just show this thing breaking apart, and then it would just be like H+ and Cl-. Yes?
This might be like a bad question.
Oh, don't go down that route. Never start with that.
Because like
Just have a question.
the two reactions we were talking about,
Yes.
they're technically the same thing.
They are the exact same thing.
Would it be wrong to say that the concentration of the like hydrogen cation and the
Hydronium cation are the same. They're the exact
They're the
same.
same, okay.
They'll be the exact same. And when we start looking at problems, and I'll probably just solve a problem where I'll show you it with the water and without the water, it's not going to change anything. And luckily it works out. Once again, this is like a shortcut way, but it's not real. I can't have H plus out there by itself. It really attaches itself onto the water to produce the hydronium cation in this case. All right, so once again, we've got our hydronium cation, and I tell you right here that you can take the H plus and also hydronium cation and use them interchangeably. And if you look at it, this reaction right here kind of shows you both ways. Both mean the exact same thing. Nothing different between the two. Here we go. Next thing to talk about is we got to talk about what is known as our conjugate acid and also what is known as our conjugate base. Now, if you look at it, there is a formal definition for this thing known as conjugate acid and also for the conjugate base. I'm here to tell you, I don't know the definition. I'm going to read it to you really quickly. I'm going to show you a way in which you don't necessarily have to commit the definition to memory. But it says right here, whatever is left of the acid after the proton has donated is called the conjugate base. So what does that really mean? It simply means that, hey, after I donated my hydrogen cation right here, whatever is left, which would be now just this A minus over here, this will be referred to as my conjugate base. Got it. If you look at it, the conjugate acid is defined as simply whatever remains of the base after it accepts the hydrogen proton. After you accept it, well, what remains is now H3O plus. This would be called my conjugate acid. Now, ask me what the definition is again. I'm going to say I don't know it. Well, actually, I did because I just read it. But anyways, I'm not using that definition. The way I'm going to look at this thing is I got like an equilibrium going on here, right? Which means that, hey, you know what? This equilibrium is going to produce some of this stuff over here. I'm going to have some of this stuff over here. And if I go in this direction right here, let me see. You're donating the H plus. You are called my acid. You're accepting the H plus. I'm going to call you my base in this case. So if somebody says, who is the acid? You're the acid. Who is the base? You're the base. But watch this. If I go in the reverse direction, all right, going in the reverse direction. I'm going this way here. Who is my acid? You're my acid, because you're donating the H plus to the A minus. So I can say you're my acid. Who's my base? You're accepting, you're my base. Which means I got a problem here, Houston. The problem is when somebody says, who is the acid? Well, HA is the acid. Hydronium cation is the acid. Well, we gotta have a way of distinguishing them. So what we do is we simply say that on the product side, instead of calling it an acid, we call it our conjugate acid. Over here, we call this our conjugate base. And that's why I don't commit these things to memory. I just look at going in the reverse direction. Instead of going just an acid, I go like my conjugate acid. You're the donator, you're the acceptor, you're my conjugate base. Once again, we had this conversation, didn't we? But I had to remember I got a son, I got a daughter, I remember their ages and all that other stuff. Too many things to memorize. I'm not sitting here and memorize this definition. I just kind of understand what's going on here. Yes?
Is that only for equilibrium?
It's going to be true. Technically, yes. But at the same time, they might ask you. And if they do, just force it to go back and say, oh, you're the conjugate acid, you're the conjugate base here. All right. Here we go. So once again, this part of the notes, I'm just going to go in and just simply say that when it comes to the conjugate acid-base pair, and sometimes they'll ask, hey, what's the conjugate acid-base pair? All you're going to do is you're going to do things such as this. You're going to say, you're my acid because you donated the H plus here. You're my base because you're the acceptor. Over here, you happen to be my conjugate acid. You're my conjugate base. And once again, that's because you're the donator going back this way. When they ask for the conjugate acid-base pair, all they're simply saying is, I want you to take those things that are kind of alike, and they're like a pair here. That's my acid, and that's kind of like its conjugate base in this case. It's like the two kind of go together. Over here, you would be my conjugate acid base pair between these two. And sometimes they'll just simply say, who's the conjugate acid base pair? Or who's the pair that goes along with HA? Well, hey, the thing that's kind of left over, the A minus. In this case, who's closest related to this one? It's going to be this one right here. It's as simple as that. So for instance, if we had something such as the following here. Say that I have HCl. And they ask me, hey, when HCl is placed in water, identify the acid, identify the base, identify its conjugate acid and also its conjugate base. Then what I'm going to do here is I'm going to go in and I'm going to do the following. Matter of fact, yes, I'll do it anyways. I'm going to go plus H2O. And better yet, what I'm going to do here. How much time? We got 3 minutes here. We'll do it anyways. All right. I'm going to put aqueous here, I'm going to put liquid here. I'm going to put an arrow right here, and I'm going to go right here and put down H3O plus aqueous plus Cl minus aqueous. And then I'm going to go in and identify my acid, identify my base, my conjugate acid, and my conjugate base. And clearly I can go in here and say, you're my acid, you're my base, you're going to be my conjugate acid, and you're my conjugate base. Dry acetic acid here. And then once we finish with this acetic acid one, then you know what your homework is going to consist of. Once again, go back, take a look at the KSP, FRQ problems, make sure you're okay, and study. Get yourself ready for that test. And once again, if you have any questions about the FRQ, by all means, come in and see me. Come in during the code period, lunch period. Let's talk about any and everything you want. Don't forget you got your prep books there. I got prep books back here. Nice thing about the equilibrium chapter is it's kind of a standalone chapter. So you should be able to go to your prep books and it should just be exclusively equilibrium. We've covered everything you need for equilibrium. All right, here we go. For the acetic acid, what you should have something that looks like the following. We're gonna have plus H2O as a liquid. You're gonna be aqueous here. This one is gonna end up producing H3O plus aqueous, plus we'll get C2H3O2 minus aqueous, because once again, the hydrogen cation is just gonna go here and donate itself to the water here. So I know you're gonna be my acid, and that was a terrible base. I'm gonna do this right here. You're my conjugate acid, and you would be my conjugate base here. All right, we'll pick up here to